All right, today we're going to talk about the tangent function. And the tangent function is the ratio between sine and cosine, because if we have a unit circle and we have a point xy and we drop a perpendicular, the adjacent side is x, the opposite side is y, and of course tangent is opposite over adjacent. So that's the definition of tangent as y over x. And because on the unit circle, the sine value is the y value and the cosine value is the x value, then tangent can be written as sine over cosine. And the last definition, m stands for slope, as in slope of a line. So if we have this terminal ray of the tangent function right here, then the slope of that line is this change in y divided by the change in x, which is noted as m for slope. So just like we did with sine and cosine, what we can do is understand the unit circle, understand the development of the tangent function by looking at terminal rays on the unit circle. So we start with a terminal ray right here on the x-axis at the point 1, 0, and then we move up a little bit more, we move up even more, and we get awfully close to the y-axis. Well, when that happens, basically we have the terminal ray having a slope of 0 when we are on the positive x-axis, having a slightly higher slope, having an even more high slope, even higher and even higher. And what ends up happening is that the slope increases as theta increases, but if we got to pi over 2, which is the positive y-axis, we would have y over x as 1 over 0, and the slope of that vertical line is undefined. That means that the tangent function is actually undefined at the angle pi over 2. Okay, so now we have an intuitive understanding that the tangent function is undefined at pi over 2. That is because in limit notation, as theta approaches pi over 2, from below or from the left, and that's what that negative sign in the exponent field means, is that we're coming from angles below pi over 2. So for example, up here we might have been at pi over 6 and perhaps at pi over 4 and then at pi over 3 and then something closer to pi over 2. As we got closer and closer to pi over 2 from theta values below pi over 2, the tangent, or the y over x ratio, got closer and closer to infinity. So let's then take a look at what happens when theta is between pi over 2 and 1. Notice here that we have a negative slope because we have a terminal ray with a negative slope, so tangent will be negative. And it is highly negative and then becomes less negative and even less negative and even less negative. And when we end up here on the negative x-axis, which is an angle of pi, the slope is 0 because there is no change in y values for any given change in x values. So what we see is that on the interval from pi over 2 to pi, the slopes transition from negative infinity all the way up to 0. So imagine that this terminal ray here, this first one, is almost a vertical line. Then the slope of that line would be undefined if completely vertical, but is close to being negative infinity because it's highly negative, and then of course it decreases or actually increases towards 0. Okay, and now as we continue around the unit circle, now this time from pi to pi over 2, you'll see that we have now a positive slope again, but very slightly positive, a more positive slope, an even more positive slope, and an even more positive slope. And of course, when we get to 3 pi over 2, we have an infinite slope again because we have an undefined spot because 1 over 0 is undefined. So each time the terminal ray is vertical, whether it's on the positive or negative y-axis, the slopes of that line are undefined, and they approach either positive or negative infinity depending on whether the terminal ray has a positive or negative slope. So that means when we graph the tangent function, we are going to see vertical asymptotes when theta is both pi over 2 and 3 pi over 2, and the fact is when theta is any multiple of pi over 2 or 3 pi over 2. So moving ever onward, this is the graph of the tangent function. And you will see here we have vertical asymptotes at all multiples of pi over 2. That's a misnomer. It's not all multiples of pi over 2. It's all odd multiples of pi over 2. Negative 3 pi over 2, negative 1 pi over 2, positive 1 pi over 2, positive 3 pi over 2. The even multiples would be the pi's, like 2 pi over 2 is pi. That's not an asymptote. Okay, so it's the odd multiples of tangent where we have our asymptotes. So here are the important features of the tangent function, and we'll make sure we get this tangent function on the screen while I talk through it. But basically, here is the transformation equation, or the parent function for tangent. We have a vertical dilation by a. In a sine or cosine function, that a value is called the amplitude. It does not have a name for tangent. It is simply a vertical dilation, and it would be inappropriate to refer to it as amplitude. Notice that the tangent function repeats every pi, and you can see the curves on the graph above. We have vertical asymptotes at all the odd multiples of pi over 2, and then in between those asymptotes we have the exact same curve. That means the standard period for tangent is pi, and so in cosine and sine, the period was 2 pi over b. In tangent, the period is simply pi over b. This plus c would be a phase shift of negative c. It is still called a phase shift with tangent. And of course, it's still called a period with tangent. We don't have an amplitude, we have a vertical dilation, and also we do not have a midline, we have a vertical translation. So if you think about it, the horizontal impacts of period and phase shift have the same vocabulary for sine, cosine, and tangent, but the vertical impacts have different vocabulary. And for tangent, we just call them vertical dilations and vertical translations. And of course, up or down by d units. Okay, so let's do a couple of examples here. We have a graph as shown, and this function, f, can be written in standard form of a tangent. So let's find the values of a, b, and d. Notice that they didn't ask us for the value of c, and that is because this curve is centered here at the origin, which means there is no phase shift. The first thing I'll do is take a look at the period. Remember, the period goes from asymptote to asymptote. So that period is pi over 2 because it goes from negative pi over 4 to pi over 4. So my b value is the main tangent period divided by, let's see, let me rephrase this actually. The period is going to be written as pi over b. Period equals pi over b. B equals pi over period. That's what we want to do. We're going to say b equals pi over period. And in our case, period is pi over 2. So pi divided by pi over 2 is multiplied by 2 over pi. And so our b value equals 2. The d value is going to be 0 because I have no vertical translation up or down. I cut through the x-axis there. And then last, it's very, very difficult to determine whether there is a vertical dilation when looking at the graph of a tangent function. So for example, when I look at this graph, I am going to take a look here and say, gosh, halfway in between the place where I cross my x-axis and the vertical tangent line should get me to 1 and negative 1. And it looks like they do, which is a standard a value of 1. So I had a b value that was 2 because it's pi over period, pi over 2, and a d value of 0. Let me just go back to this. We know that tangent of pi over 4 equals 1. So on a standard tangent function, and I'm going to pull up the tangent function we had above, on a standard tangent function, pi over 4 maps to 1. Notice that pi over 4 is halfway in between the place where tangent crosses the x-axis and each asymptote. So I know that I have a vertical dilation if, for example, this value was pulled down further or pushed up further. So while it is very, very difficult to determine from the graph of a tangent function, whether or not there's a vertical dilation, I think we can pretty well say that this one does not have one because the input value halfway between the x-intercept and the asymptote appears to map to 1, which is what it would do on a standard tangent function. Okay, my next question states, the function h is defined by 4 tangent 2x plus 5. What is the period? Well, remember that period equals pi over b, and in our case here, b is 2, so the period is pi over 2. In fact, it's the same period as this one we just did right above it. Alrighty, so moving on to the next problem. We'll do example 3 first. We have here, let g be the function defined by g equals 2 tangent x over 3 minus 1, which gives us the vertical asymptote. So that's going to depend on, it would depend on any horizontal transformation, so a period and a phase shift. There is no phase shift, which is super helpful. And I know that my b value, which is 1/3, is pi over period. And so that means my period is pi over 1/3, or 3 pi. So if my period is 3 pi, I need to be having intervals of 3 pi for every asymptote. And I'm going to have my first asymptote, by the way, on the tangent function, on the standard tangent function, I have my main period goes from negative pi over 2 to pi over 2, crossing the origin and always increasing. So that's important to note because when I stretch my period, I basically have the same shape. I have no phase shift, so I'm still intersecting the origin, but now I know that this asymptote is at negative 3 pi over 2, and this asymptote is at 3 pi over 2. Okay, and then now we're going to look at this graph, and we're asking which is the equation. Well, first thing I always look at is where is that inflection point on the graph, because that tells me if I have a vertical shift up or down, and we clearly have a vertical shift down, so we're going to go with either A or C. And then the only thing different now is the period. It looks like my period goes from negative pi to pi, which is 2 pi. So my b value is pi over 2 pi, which is 1/2. And I land on A being my final answer. Okay, and the last problem in this fairly short lesson says, find the values of the expressions using the unit circle. Well, what I like to do is, I like to just remember that pi over 4 is rad 2 over 2, rad 2 over 2 for my x and y values. Pi over 6 is rad 3 over 2, 1/2. And pi over 3 is 1/2 rad 3 over 2. And remember, tangent is always y over x. So the easiest ones to handle are the ones that are pi over 4, because y over x is rad 2 over 2 over itself. So then I just have to determine whether my answer is positive or negative 1. In the first quadrant, my tangent value will be positive because of all students take calculus. All angles, all trig ratios are positive in the first quadrant. My only other pi over 4 family is 7 pi over 4, which maps down into the fourth quadrant, and tangent will be negative in that quadrant. So pi over 6 will be 1/2 over the square root of 3 over 2. And when I work that out, I end up getting 1/2 times 2 over rad 3, which is 1 over rad 3, which is rad 3 over 3. But in this class, you don't have to rationalize. So I start with rad 3 over 3 as tangent pi over 6. And I have one other pi over 6 family. 5 pi over 6 is in the second quadrant, so tangent will be negative. My next family will be the pi over 3 family. Working here, I have rad 3 over 2 over 1/2, which simplifies to actually just rad 3. So tangent of pi over 3 is simply rad 3. Tangent of 4 pi over 3, since that is in the third quadrant where tangent is also positive, that will also be rad 3. And then my last two are quadrantal angles. Tangent 3 pi over 2, that is on the negative y-axis, and tangent is undefined where we have a vertical axis because the slope of a vertical line is undefined, and tangent of pi is 0 because I have a 0 slope for that terminal ray.